How do I make algorithmic strategies flexible? One of the challenges of algorithm design is to make the algorithms flexible enough to handle different types of inputs and outputs, without compromising on efficiency, correctness, or readability. In this video, I will explain some of the principles and techniques that can help you achieve this goal. First, let's define what we mean by flexibility. Flexibility is the ability of an algorithm to adapt to different situations or requirements, such as different data formats or structures, different assumptions or constraints, different performance or quality metrics, different user preferences or expectations. Flexibility can be measured by how easy it is to modify, extend, or reuse an algorithm for different purposes or scenarios. Second, let's see why flexibility is important. Flexibility can have several benefits, such as improving the usability and user satisfaction of an algorithm, reducing the development and maintenance costs of an algorithm, enhancing the robustness and reliability of an algorithm, increasing the generality and applicability of an algorithm. Flexibility can also have some trade-offs, such as increasing the complexity and difficulty of an algorithm, reducing the efficiency or optimality of an algorithm, introducing potential errors or bugs in an algorithm, decreasing the readability or understandability of an algorithm. Therefore, flexibility should be balanced with other design criteria, such as simplicity, efficiency, correctness, and readability. Third, let's explore some of the ways to make algorithmic strategies flexible. Here are some common strategies that can help you design flexible algorithms. Parameterization. This means using variables or parameters to control the behavior or output of an algorithm. For example, you can use a parameter to specify the sorting order, ascending or descending, of a sorting algorithm, or the precision, number of decimal places, of a numerical algorithm. Parameterization can make an algorithm more customizable and adaptable to different user preferences or expectations. Generalization. This means using abstract or generic data types or operations to handle different types of data or tasks. For example, you can use a list or a set to store any kind of data, or a function or a lambda expression to perform any kind of computation. Generalization can make an algorithm more versatile and applicable to different data formats or structures. Modularization. This means dividing an algorithm into smaller and independent sub-algorithms that can be combined or reused in different ways. For example, you can use a modular arithmetic algorithm to perform arithmetic operations on large numbers, or a modular exponentiation algorithm to compute powers efficiently. Modularization can make an algorithm more manageable and maintainable, as well as easier to test and debug. Recursion. This means defining an algorithm in terms of itself, by breaking down a problem into smaller and simpler subproblems that can be solved by applying the same algorithm. For example, you can use recursion to implement a binary search algorithm, or a factorial function. Recursion can make an algorithm more elegant and concise, as well as more expressive and powerful. Iteration. This means repeating an algorithm until a certain condition is met, such as reaching a desired output, a fixed point, a convergence, or a termination. For example, you can use iteration to implement a linear search algorithm, or a Newton-Raphson method. Iteration can make an algorithm more efficient and robust, as well as more adaptable and scalable. Randomization. This means using random numbers or choices to introduce some variability or unpredictability in an algorithm. For example, you can use randomization to implement a Monte Carlo simulation, or a randomized quicksort algorithm. Randomization can make an algorithm more realistic and practical, as well as more diverse and creative. These are some of the common strategies that can help you design flexible algorithms. Of course, there are many other strategies that can be used depending on the specific problem domain or context. The key is to understand the problem well and choose the appropriate strategy that suits your needs and goals. To illustrate how to design flexible algorithmic strategies, let me consider some examples. Example 1. A sorting algorithm that can sort any type of data. A possible strategy is to use a comparison-based sorting algorithm, such as merge sort or quicksort, that relies on a generic comparison function that can compare any two elements of the data. The comparison function can be defined by the user or by the data type itself, and it should follow some basic rules, such as being consistent, transitive, and reflexive. This way,
The sorting algorithm can sort any data that has a well-defined order relation, such as numbers, strings, dates, etc.
Example 2. A search algorithm that can find any item in a collection. A possible strategy is to use a linear search algorithm that iterates through the collection and checks each element against a target value. The target value can be anything that can be compared with the elements of the collection, such as a number, a string, a function, etc. The comparison can be done using a generic equality function that returns true if two values are equal and false otherwise. The equality function can be defined by the user or by the data type itself, and it should follow some basic rules, such as being symmetric and reflexive.
This way, the search algorithm can find any item that matches the target value in any collection that supports iteration, such as arrays, lists, sets, etc.
Example 3. A pathfinding algorithm that can find the shortest path between 2 points in a graph. A possible strategy is to use a graph traversal algorithm, such as breadth first search or Dijkstra's algorithm, that explores the graph from a start point to an end point. The graph can be represented by any data structure that stores nodes and edges, such as an adjacency matrix, an adjacency list, etc. The edges can have weights that indicate the cost or distance of moving from one node to another. The weights can be any numeric values that are positive and additive. The pathfinding algorithm should keep track of the current distance and the previous node for each visited node, and update them accordingly when finding a shorter path. This way, the pathfinding algorithm can find the shortest path between any two nodes in any weighted graph that has no negative cycles. These examples show how to design flexible algorithmic strategies by using generic functions and data structures that can handle different types of inputs and outputs. However, this is not the only way to achieve flexibility. There may be other ways to design algorithms that are more suitable for specific problems or domains. The key is to understand the problem well and identify its essential features and variations.
I hope this video has given you some insights into how to make algorithmic strategies flexible.
If you have any questions or comments, please feel free to share them below. Thank you for watching.